In this video, we're going to learn how to use a finite state machine to better organize the controller for our game. So a state machine or finite state machine can be used to allow us to take sequences of events and order them, for one, and for two, it can allow us to have a script set to a certain mode and perform actions that are specific to that mode, and then move in and out of that mode and other modes. So in this game, we have a ball on a platform, and we're able to rotate the platform with arrow keys. And the camera will start off by panning into the scene and then pause briefly and start to follow the ball as it moves around the platform. And then when we quit the game, we'll look up at this cube up here, which has some credits on it. So let's take a look at how the game runs right now. So the camera pans in and then starts to look at the ball. And now if I use the arrow keys, I can get the ball to move a little bit, and we notice that the camera is following the ball as it moves. And if the ball falls off, the camera will follow it down, and then the position of the ball will reset to the start. We can bring it close, maybe. It's actually kind of a hard game. So let's try and bring it closer to the camera. And we get the idea. So then if I hit escape, that means that I'm quitting the game, and we'll pan up to some credits. And that's our game. So we had a few different things happen, or different states. So the first state was the introduction, where the camera was panning up the game board, right? And then the second state could be considered that we paused for a moment and let the camera just look at the game board. Then after the pause, it went into the play state, where the camera would follow around the ball. And then when we hit escape, we went into the final state, which was to look up at the credits. So we'll see in that this game is actually all managed by one script that's attached to the camera, and that's called Game Controller. And we've included references to the ball, the platform, and the credits as transforms. So let's take a look at that script. Here's the Game Controller script. It starts out with public members that define the ball, the platform, and the credits, as we saw in the inspector. And this comment is actually wrong. So this is the cube that displays the credits. After that, we have an enumeration, or enum, and this enum allows us to create several identifiers that are grouped within a single structure, which is this game state. So we've made a new type called game state, and this new type can assume these four values: intro sequence, pause before start, playing, and look at credits. You may or may not have seen enumerations before. Hopefully you have. If you haven't, they're just like what I said. You're creating a new type. It's like saying a new class, for example. And the new type can only assume certain values that you define within these curly braces. So in this case, we have four different values that can be assigned to this type. So I'll go down into start, and I'll say game state equals, and then we'll see that we have game state dot, and we have these 4 different values that we can assign to a game state variable, right? So this is a way of enumerating or providing a value to different textual concepts that we have. So turning that into discrete values. And then, so after the game state, we define a game state called current state, which is going to be the current state of the game. It's either in the intro sequence, the pause before start, the playing, or the look at credits mode. And finally, we have a float that represents the last time that the state was changed. Okay, so at the start, what we do is we initialize the current state to the intro sequence. So we've actually defined a method below that allows us to set the current state. So I say set current state game state dot intro sequence. So if we look at below the set current state method, it accepts a game state and sets a current state equal to that game state. But additionally, it updates the last state changed variable to be time.time. So whenever we made this call, that's going to be the last time that the state was changed. And we can see in the method below that's useful for getting the elapsed time that we've been in the current state. So we have this get state elapsed, and this returns a float which represents the amount of time that we've been in one of these 4 states: intro sequence, pause before start, playing, or look at credits. So this will let us know, it's an easy way of letting us know how long we've been in the current state. Because a lot of times we might want to change out of a certain state after an amount of time, a specified amount of time has elapsed. Okay. Now moving on, we have the update routine, and this is where most of the things that happen in the game are implemented. So the first thing we do in the update routine is check if the ball position y component is less than -20. If that's the case, then we are detecting that the ball has fallen off the game board and fallen fairways, so we're going to reset the ball. So then we say ball.position equals vector3.up. So vector3.up is the vector 0, 1, 0. So this is just a shorthand of saying 0, 1, 0. So that's the origin, and then it has to be on top of the game board by a little bit. So we put it 1 unit above the world origin, or 0, 1, 0. So vector3.up. And then we also want to make sure that, so that ball is falling, and it might even be moving, with some velocity in the x and z dimension. And we want to make sure that we reset that velocity when we reset the position, or else it might, start to move based on physics as soon as we put it in its new, put it back at the origin. So to do that, we get the rigid body component of the ball, which is ball.rigidBody, and then we set that component's velocity to be vector3.0, so 0, 0, 0. Okay, so that's how we reset the ball. Now let's look at how we perform or implement the different states that we're in. So what I have here is a switch statement. So we're going to switch the current state to see what state we're in. Okay, and then we're going to have code that executes for each state that we could possibly be in. So I'm sure you've seen switch statement before. It's essentially a way of saying if, else if, else if, else if, else if. So we're saying if the current state is intro sequence, then we're going to perform this code. else if the current state is pause before start, we're going to execute this, etc., for each of the 4 states. So if we're in the intro sequence, what we're going to do is translate the camera position, which is what the script is attached to. So our transform, we're going to translate it up, right? And the rate, the vector we're going to supply to translate is going to be vector 3.up, so 0, 1, 0, right? Times 2, so that makes it 0, 2, 0. And then we're going to multiply that by time.delta time. So that means we're going to translate it at a rate of 0.20 per second. Okay? And using the dot multiplication on vectors can be useful to isolate certain portions of the vector. So by doing the vector 3.up, which is 0, 1, 0, we've isolated the y component of the vector and then multiplied it by a scalar, which is 2, to increase the y portion of the vector, right? And so this is going to translate the camera position up at a rate of 2 units per second. Okay, and then what we're going to, then we have an if statement that says if get state elapsed is greater than 2.5, and if we recall, get state elapsed is going to return how long we've been in the current state, which is intro sequence. So if we've been in the current state more than 2.5 seconds, then we're going to change states. And in this case, we're setting the current state to pause before start. Okay, so when this line executes, we will no longer run the code in this state. So we'll stop translating up, and we'll go now to this state, which is pause before start. In pause before start, we don't do anything. It's just a waiting state. So we only have one line, which is or one block of code, which is if get state elapsed is greater than 1.0, then set the current state to GameState.playing. So that means that we're going to go from the intro sequence, we're going to go to this pause before start state, and then we're going to stay in that for 1 second. So we're not going to do anything for 1 second, and then we're going to set the current state to playing. Okay, and then once we're in the playing state, we're going to be following the ball around. So the first thing we do in the playing state is calculate a target rotation to look at the ball, and we use quaternion.look rotation. And we supply that, which returns a rotation that matches, that aligns along a certain direction. So that means like how to rotate an object so that it will look at or look in a certain direction. And the direction we want is the ball's position minus our position. So we're subtracting our position out of the ball position, and what's left is our is the relative position of the ball to us, right? And this might be too meta, but so normally the ball positions in respect to the origin, right? But if we subtract out our position, then the ball position is going to be relative, the resulting position is going to be relative to us. So it gives us a direction to, from us to the ball. Okay? And so after we have that target rotation from look rotation, we then set our rotation to match that, and we do that over time. So we say quaternion.lerp from our current rotation to the target rotation, and we pass it time.delta time. Okay, So time.delta time is just going to slow our roll, so to speak, so that it doesn't happen instantaneously. It's going to happen, in conjunction with the frame rate. So at a rate of one per second, right? Then we go. The next thing we do is set a rotation rate, and we're going to get the input for rotating the platform that is underneath the ball. So if we have a key, and we say get key, so it's not get key down, not get key up. It's going to be get key. So it's going to be every frame that key is pressed down. And we say if it's the left arrow, then platform.rotate, and we pass it a new vector 3. And if it's the left arrow, then we want to rotate around the Z, and we're going to rotate in a positive direction. So time.delta time times the rotation rate, which is 20 in this case. And then if it's the right arrow, we're still going to rotate around the Z-axis, but it's going to be negative. Then if it's the up arrow, we're going to rotate around the X-axis in a positive. And if it's a down arrow, we're going to rotate around the X-axis in the negative direction. Okay, so that provides 4 axes of rotation that we can rotate. And you notice that we used if statements here. So we can combine left and up, or left and down, or right and up and right and down, and we'll get diagonal rotations. So lastly, we check if the get key down, not get key, but get key down, the escape key. So we've hit escape. That means we want to exit the game. Then we set the current state equal to game state dot look at credits. So now we're going to look at the credits. And finally, we have the case when we're in the state look at credits. And in this case, we're going to set the rotation equal to the look rotation from us to the credits, which is that cube above us. So credit position dot or minus our position, which gives us a direction. In this case, it's going to be up, but we can theoretically put the credits elsewhere. And we calculate that look rotation, and then we lerp towards that at a rate of 1 per second, which is just time.delta time, and the subtext is times 1, right? And that's all. That's our entire code for this game. So let's go back and look at how it behaves one more time. Hit play. Goes up, pauses, turns to look at. We're able to press the keys, which we wouldn't have been able to press the keys right off the beginning, because those statements wouldn't have been accessible in that state. And then we hit escape, and we're going to look at the credits. One last thing to note might be how these two, the ball and the platform, are set up in the physics engine. So if we look at the ball, you could probably guess how that's set up. So we have a rigid body. So we have a sphere collider, first of all, that's set to is trigger false. So it has a presence in the 3D or in the physics simulation. And then the rigid body, which means that the physics engine is going to track it. It's using gravity. It's not as kinematic, rather. So that means that gravity affects it. The physics engine is going to move it, and it's pretty standard. Then when we look at the platform, it also has a box collider with is trigger set to false, but it also must have a rigid body because we're going to be moving the platform, and the physics engine therefore has to be able to track it. However, with this rigid body, we're going to set it to is kinematic because we're going to be moving it manually, right? So we're going to move this manually, but we want the physics engine to know about how we've moved it every frame. So this gives it that information, and it's able to update the physics simulation with its new rotation, and that's how it's able to affect the ball, right?